Section 11.1b, we're going to do one of these problems, and it says number 20. It says a sub n equals 2 plus negative 1 to the n over n. And it says to calculate the 4 decimal places, the first 4 terms. So a sub 1 is 2 plus negative 1 over 1. That's 2 minus 1, which is 1. A sub 2 is 2 plus positive 1 over 2. So 2 plus a half is 5 halves. A sub 3 is 2 plus negative 1 over 3. So 2 minus a third is 1 and 2/3, which is 5/3. A sub 4, we're supposed to calculate the first 10 terms. 2 plus positive 1 over 4. So that's 2 1/4, which is 9/4. A sub 5 is 2 plus negative 1 over 5. That's 2 4/5. Sorry, that's 1 4/5. That would be 9 over 5. And a sub 6 is 2 plus 1 over 6. That's 13 over 6. And a sub 7 is 2 minus 1 over 7. So that would be 2 and 6/7. I'm sorry, 1 and 6/7. That's 13 over 7. So as you can see, these are getting smaller. Let's look at the graph. One, 2, 3, 4, 5, 6, 7. Okay, so 1 is 1. 2 is 5 over 2. That's 2 1/2. 2 is 2 1/2. 3 is 5/3, which is 2 2/3, which is 2.6, so it's a little higher. 4 is 9 over 4, it's 2 1/4, so it's going to come down. And a sub 5 is 9/5. It's nearly 2. 1, 2, 3, 4, 5 is nearly 2. Can't make that dot happen. A sub 6 is 13 over 6. It's 2 1/6. It's actually a little lower than the last one. So let's try that again. 3, 4, 5, 6. So it's a little lower than 2 1/4. Then we have 13 over 6. So it's a little over 2. We just did that 2 1/6. And the other one is 13 over 7, so it's almost 2. So as you can see, if we were to draw the line across 2, we're kind of going in between them. So this one is kind of approaching 2. So we would say it converges to 2 because it's bouncing back and forth and coming at 2. Now, the reason I wanted you to see kind of what a graph did. So here we have a definition. A sequence A sub n has the limit L, and we write the limit as n approaches infinity of A sub n equals L. We don't generally use this notation much, so it says or. This is the notation that we use. And that says if we can make the terms A n as close to L as we like by taking n sufficiently large. On the last problem, we would say that the limit is 2. It gets closer and closer to 2. If the limit as n approaches infinity of A n exists, we say the sequence converges or is convergent. Otherwise, the sequence diverges or is divergent. Very similar to the improper integrals that we did at the end of chapter 7. So you can see in this first graph that we're kind of, if we were to connect the dots, we're coming down across and approaching that value of L. Now, we don't connect the dots. I just wanted you to be able to see as I talk to you about it. And this one, you can see that it kind of bounces back and forth across it, kind of oscillates across the line, and it's getting closer and closer and closer to that line L. So we would say the limit as n approaches infinity of A n is L. Now if you see this is 2 1/2, and this is almost 2. It's 1 2/3, and this one is 2 1/4, and this one is almost 2. It's 2 4/5. And this one's 2 1/6, and this one is nearly 2, so it's 1 6/7. So as you can see, we're getting closer and closer and closer, so this one does converge to 2. Sometimes it's easy to look at the numerical values, and sometimes it's easier to look at the graph or the limit. So we're going to look at a couple of these. There's a couple, let's look at this limit a little differently. So here you can see that down here we have a more precise version of definition 1. So we have a sequence, here we have the limit as n approaches infinity of an is L. If for every epsilon there's a corresponding integer such that for n greater than n, then a minus L is less than epsilon. That's the way you did it back in chapter 2. That's why it says compare. So the epsilon delta version of a limit. They illustrate this by showing you that your limit gets really close in this value in here. And you can see down here we have the L plus epsilon and L minus epsilon, and we're in that value. If you'd like to read it, feel free to pause the video and do so. If you were to compare this with chapter 2, the only difference here is that you have n as an integer, because we had where we could have any value of x. When we're working in sequences, n is the term number, so it is always an integer. So here we have this theorem, and it says the limit as x approaches infinity of f of x equals L, and f of n equals a sub n, where n is an integer, then the limit as n approaches infinity of an is L. So it kind of makes sense that if you were to connect the dots and look at the graph, as they did here, if we were to connect the dots and look at this graph, then it's saying the y values for the graph correspond to the values for a sub n. So you still have your limit. So the limit as x approaches infinity of 1 over x equals r, when r is greater than 0 by theorem 2.65. What that really says is the limit as x approaches infinity of 1 over x to the r equals 0. But you have to remember this means 1 over infinity, and 1 over infinity approaches 0. So then the limit as n approaches infinity, right here, line number 4, of 1 over n to the r equals 0 if r is greater than 0. So if an gets large, as n becomes large, we say that the limit as n approaches infinity of a of n equals 0. So here's the definition in number 5. The limit as n approaches infinity of a sub n equals infinity means for every positive number m, there's an integer n such that if n is greater than capital N, then a sub n is greater than capital M. So down here we say the series is divergent. Sorry, the sequence. The sequence is divergent, but in a special way. So we say the sequence of a sub n diverges to infinity. So pause your video for a minute, and these are the limit laws for sequences. They look very much like your limit laws for just normal limits. Remember, the main difference here is that we're dealing with n as an integer, so we're dealing with a pattern of numbers. So pause the video, pay attention to them. You should be familiar with these laws already. Here we have the squeeze theorem, and it can also be applied for sequences. So if b sub n is between a and c, the pink one in the figure, for all n is greater than n sub 0, and if the limit of n approaches infinity of a sub n equals the limit as n approaches infinity of c sub n, which equals L, then the limit of b sub n also equals L. So if the limit of the bottom one, if the limit here of that set of numbers is equal to the limit here of the blue set of numbers, then the limit of the red ones in the middle is the same as well, by the squeeze theorem. That comes in handy sometimes. We have another useful fact we're going to look at. And this is a theorem. If the limit is n approaches infinity of the absolute value of a sub n equals 0, then the limit of a sub n also equals 0. So let's look at a couple problems here. This one says find the limit as n approaches infinity. And the problem says n over n plus 1. Now, if you remember in limits back in chapter 2 in Calc 1, your first technique is to plug and chug. But if you plug it in, you get infinity over infinity, which is an indeterminable form. So what you want to do is you want to think about your other techniques. Factor and cancel doesn't work. But you can divide by the highest power of n in the denominator. So that is n. So n over n and n over n plus 1 over n. You divide every term by the highest power of your polynomial in your denominator. So we have 1 over 1 plus 1 over n. Now when you plug in infinity, this term goes to 0. So we end up with 1 over 1, which is 1. So that means the limit of the sequence is 1. So that means we're approaching 1 as we develop those. Now if you looked at a sub n would be 1 over 2. And a sub 1, a sub 2 would be 2 over 3. And a sub 3 would be 3 over 4. And a sub 4 is 4 over 5. So can you see that we're getting closer to 1? This would be 5 over 6, and so forth. So you can use it to determine the fact that it converges to 1. So let's look at the next one. It says a sub n equals n over the square root of 10 plus n. So let's look at the limit as n approaches infinity of n over the square root of 10 plus n. So if we plug in infinity, we have infinity, and infinity plus 10, and the square root of that is still infinity. Now you're supposed to divide by the highest power of n in the denominator, but you want to do integer powers. So let's divide by n. So we're going to put n over n here. And the square root of 10 plus n over n. Well, if you think about that, we have the limit as n approaches infinity. And here that makes 1. And when you put it inside the square root, notice that n equals the square root of n squared. So we have 10 over n squared plus n over n squared inside the square root. So that means we have the limit as n approaches infinity. We have 1, here we have 10 over n squared plus 1 over n. Now 1 over n approaches 0 and 10 over n approaches 0. So we technically have 1 over 0, and in the limit world that is infinity. So this is divergent. So it's divergent because our limit approaches infinity. So it says the limit as n approaches infinity of natural log of n over n. When you plug in infinity, the natural log of infinity is infinity, and you have infinity on the bottom. That's indeterminate form. So the best way to do this one is L'Hopital's rule. We could actually go back and do L'Hopital's rule on the first one. It's easier. But L'Hopital's rule says you take the derivative of the top separately from the derivative of the bottom, not quotient rule. So the derivative of natural log of n is 1 over n, and the derivative of n is 1, not n. Let's try that again, 1. So we have the limit as n approaches infinity of 1 over n, which is 1 over infinity, which approaches 0 in the limit world. So this one converges. So make sure that you are careful about your convergence and divergent and convergent. But go back and double check your L'Hopital's rule and brush up on that. The next one says determine if an equals negative 1 to the n is convergent or divergent. So think about the terms 1, 2, to the third power, to the fourth power, to the fifth power. Oops, and I wrote 5, to the sixth power, and so forth. So this is an alternating sequence where the values are just 1. So we just have positive and negative 1 back and forth. If you were to look at the graph, it would just bounce back and forth exactly at 1 and negative 1. It's just going back and forth. So this one is not convergent. It doesn't come to a value. So since it's not convergent, then it is divergent. This one says the limit as n approaches infinity of negative 1 to the n over n. So we know it's alternating, the negative 1, but remember the theorem we looked at? This theorem is going to come in helpful here. So let's look at the limit as n approaches infinity of negative 1 to the n raised to the n power absolute value. So if I look at the absolute value, then what I'm really looking at is the limit as n approaches infinity of 1 over n. So that's 1 over infinity, and the limit world, that's 0. And based upon the theorem above, then we can say the limit as n approaches infinity of negative 1 to the n over n is 0 as well. So this one is convergent. Convergent or converges. Either way is good. Theorem 7 says if the limit as n approaches infinity of a sub n equals L, and the function is continuous at L, then the limit as n approaches infinity of f of a sub n equals f of L. So one example that we can see this, it's interesting here is the function notation on both sides. So here's an example of one. It says the limit as n approaches infinity of sine of pi over n. So what we're looking at here is the sine function is continuous at 0 and everywhere. So based upon this theorem, we can start, instead of starting with the limit, we're going to move the sine function outside. So we're going to say the sine of the limit as n approaches infinity of pi over n. So when you look at this, now you can take the limit of pi over n, and what we have then is we have the sine pi over infinity, and remember this approaches 0. So sine of 0 is 0. And that's why we need to look at the fact that it's continuous at 0. Because we're continuous at 0, this step is allowed, and the sine is actually at 0. So this is a convergent sequence. Look at the sequence r to the n power. So if we look at the limit as n approaches infinity of r to the n, let's consider values for r. If r is 1, let's look at it this way, as n approaches infinity. If r is 1, then 1 to the any power is 1. So let's look at the value if r is 2. So this one is divergent. It is very large. 2 to the infinity power is very large. 3 to the infinity power is very large. 4 to the infinity power is very large. So those are all infinity. Let's talk about a fraction. So if we have n approaches infinity of 1/2 to the n power, so that means we have 1/2 to the, 1/2 to the n. That means we have 1 over a very small number. So we have 1 over 2 to the n, which is 1 over infinity, which approaches 0. So when you look at r to the n, what we find is the limit as n approaches infinity of r to the n equals infinity if r is greater than 1, and 0 if r is between 0 and 1. So then think about -1. if negative 1 is less than r, which is less than 0, then really that's the same as 0 as the absolute value of r is between 0 and 1. So it's the same rules as above. So we can say the limit is n approaches infinity of the absolute value of r to the n. And the limit, let's put that here. The limit as n approaches infinity of the absolute value of r to the n equals 0. So what they've done is, this means that we could add to this value here, and they put it in a nice pretty box in your book. So the sequence is convergent if negative 1 is less than r, which is less than or equal to 1, and divergent for all other values. And as you can see here, now this is used for reference, especially for when you're working with things like the squeeze theorem, etc. Question 10, a sequence is called increasing if one term is smaller than the next term. So if A1 is less than A2 is less than A3, that makes sense. And it's decreasing if the smaller number and then it's a larger number. And a sequence is called monotonic if it's either increasing or decreasing. So we say it's monotonic sometimes and don't worry about if it's going up or down, but that tells us that it is either increasing or decreasing. So monotonic is the phrase we use. And then we have a couple more terms. It's we also have the terms bounded above and bounded below. So if it's bounded above, that means that they're all smaller than a number, and bounded below means all of your values are below a number. The one we did earlier where it alternated back and forth around the number 2, that is neither of these. But if we looked at a sequence where, let's say we have 1/2, we looked at this one, and then 3/4, and then 4/5, and then 5/6, and then 7/8. It's closer and closer to 1, but it never goes above. So it's bounded here, and it's bounded by 1. It's bounded above because they're all less than 1. So those are the terms you need to pay attention to. The bounded above, the bounded below, the increasing, decreasing. So that leads us to one more theorem. I think it's the last one. Crazy amount of theorems in this unit. So here's the theorem, and it says that the monotonic sequence is every bounded monotonic sequence is convergent. And if you think about that, it really makes sense, because here we have an increasing sequence that's bounded above by L, so it's monotonic and it's bounded, so it converges to a value. So that theorem makes sense, and you'll be able to see this happening in some of the problems. Now, some of the problems say determine if it's increasing, decreasing, and I think we've handled all of the terms, but look at this sequence. It says 3 over n plus 5. So the first term, a sub 1, is 3 over 6, which is 1/2. A sub 2 is 3 over 2 plus 5 is 7. A sub 3 is 3 over 3 plus 5 is 8. A sub 4 is 3 over 4 plus 5 is 9, which is 1/3. So if you look at this, 1/2 is 0.5, decimals, and 3/7 is 0.42 something-ish. I'm rounding off, probably not well, it's in my head, I'm sorry. 3/8 is 0.375, and 1/3 is 0.3 repeating. So 0.5 is larger than 0.42, which is larger than 0.375, which is larger than 0.3 repeating. So this is decreasing. This is a decreasing sequence. Number 36. It says a sub n equals -1 to the n plus 1 times the n over n plus the square root of n. Now, when we look at this, we want to look at the limit as n approaches infinity. And we want to look at the absolute value because it's an alternating sequence. So when we look at the absolute value, that means we've got all this, but it equals the limit as n approaches infinity of n over n plus the square root of n. Now, if you plug in infinity, you have infinity over infinity, indeterminate form. So you have to try a different technique. Earlier, we divided by the highest power of n in the denominator. We could do that. So we could do it that way, or we could use L'Hopital's rule. Let's divide by the highest power of n in the denominator. So we have n, all of this, the square root of n over n. So then we have the limit as n approaches infinity of 1 over 1 plus, this would be the square root of n over n squared. So we have the limit as n approaches infinity. We have 1 over 1 plus 1 over n. Now, the square root of 1 over n goes to 0. So here we have 1 over 1. But if you go back to that theorem, it says as we approach 0. Now, the theorem that says we can use the absolute value is only true if this absolute value equals 0. Then the limit of the original problem equals 0. But neither of these cases applies. So what we have here is this is the limit of all of it except for the alternating part. So let's put that back in. We have the limit as n approaches infinity of negative 1 to the n plus 1 times n over n plus the square root of n. Now the limit, using our limit laws, we can multiply the limits. So we have the limit as n approaches infinity of negative 1 to the n plus 1 times the limit as n approaches infinity of n over n plus the square root of n. Now we know that this value right here, the second limit is 1. So 1 times anything is 1. So we have this limit, but this is an alternating limit, so this is divergent because it does not converge to a value. Divergent. So pay attention to the things that you know and that you've been given to use. Let's do one on increasing and decreasing. So let's look at number 75. It says a sub n equals n times minus 1 to the n power. Now, this minus 1 to the n power means we're alternating. And alternating means I'm bouncing back and forth across some line, such as this right here. So once you start bouncing back and forth, whether you're going up or if you're coming down towards it, either way, that's not increasing nor decreasing. So this is not monotonic. So it's not monotonic. That means it's not increasing nor decreasing. So let's look at the n value. A sub 1 means negative 1. A sub 2 is positive 2. A sub 3 is negative 3. A sub 4 is positive 4. So the limit as n approaches infinity of n is infinity. So it's divergent, which means it's not bounded because it has to converge to a value to be bounded. So this one is not monotonic and it's not bounded. So now I think you have everything you need to do this lesson. Thank you and have a great day.